All right, so the question here is how do we measure a SQUID? So until now, when we measure a device electrically, we never asked ourselves the question, do we impose a voltage and measure a current, or the other way around? And the reason for that is that most of the devices that we measured are linear. But in the case of a SQUID, the IV characteristics are not necessarily linear, and it depends very much on the characteristic of the SQUID. For example, a SQUID could have an IV that looks like this. So I will take another color here. So if you're below a certain current, you're in the superconducting state, so you have zero voltage. So you're along this line here, okay? Zero voltage, until you reach the critical current here. And then what happens? So two different scenarios can happen. One is that at the time that you reach a critical current, so there's no more Cooper pairs available to produce supercurrent. So what happens is that voltage start to appear, and voltage tend to break Cooper pair. So as a result, you will get less and less current, this is a little counterintuitive because it's essentially a negative differential resistance. But and this is where the whole problem stems. But so then there is a negative differential resistance, and if I continue to raise the voltage, at some point the normal ohm conductance will start to dominate, and then I will reach some sort of a linear slope, which corresponds to the resistance, the normal stud resistance of the device. And in principle, this should cross zero, as Ohm laws prescribes here, okay, at least in this way. So now you see that with this graph, you see that actually imposing the voltage and measuring the current, or vice versa, is not exactly the same. Let's look at it carefully. So if I impose the voltage, so I have a problem here. It's multi-valued. There is a lot of values of zero voltage, but except the zero voltage, I see that here it's single valued, here it's single valued, and so on. Okay, for every point here along this line, if I impose the voltage and measure a current, except at that zero voltage, I have only a single value function. Now, let's assume I would do the opposite. Let's assume that I would impose the current and measure a voltage. Now, I don't have a problem in the zero voltage state, so I impose, let's say, this current, and I get 0 volts. I impose a larger current, everything is fine. The problem arises when I'm here. Here, if I want to raise the current a little more, I can't. I can't without staying at 0 voltage. The only way I can raise the current is by increasing the voltage significantly, meaning I'm jumping to this point. Now this is a big jump that will look to us like instantaneous, and most of the time the SQUID in this region is not that good. And in fact, like if we do things carefully and we reduce the current from this point, we will reach this minimum here, in which the only way I can reduce the current is by snapping back to 0 voltage. And this is called the switching current, and this is called the retrapping current. And the IV that you will really measure will have this shape. We'll have a shape like this. Okay, with this being the switching current, and this is the retrapping current. Okay, so in general, we don't want our device to be hysteretic. So we would like to do a voltage bias and measure the current. So we said before that the condition would be that we sort of impose a voltage and measure a current. So how do we do this in practice? So voltage sources are quite common in the lab. So you can draw them as an element like this, and they're quite common. So you can say, okay, so let's hook to my SQUID. This is the symbol of a SQUID. Let's hook up a voltage source and let's measure the current. The current, to measure the current. Okay, so how do you measure the current? The current typically is measured by measuring the voltage on a known resistor. Okay, so I would need to put here a resistor and measure the voltage here. And then I know the current, okay, which is just V divided by R is the current. And the voltage I set, and that's it. What is the problem here is that in order for me to have a good, so the smallest current is set by the value of this resistance. So if I have a very large resistor, I can measure very small currents. But if I have a very large resistor here, what am I doing here is essentially doing a current bias and not a voltage bias. Why is that? The resistance here are, even in the normal state, typically very small, of the order of an ohm or something like that. And here, if you want to have a good readout, let's say we want to be able to resolve so let's say here what I'm measuring is V, okay? I'm measuring V, and let's say I can measure to 1 microamp, and I want to be able to measure let's say a nanoamp, so I would need to put a kilo ohm, right? So if my current here is of the order of a nanoamp, I need to put a kilo ohm so that this will be of the order of my sensitivity, which I set to about 1 microvolt. So if I put here 1 kilo ohm, this resistor, this 1 kilo ohm resistor will be much larger than even the normal state here. So essentially this you can disregard from the circuit. Whatever happens here doesn't matter, and the current is set by this resistor and the voltage that you apply here. So effectively what you're doing is doing a current bias. So that doesn't work. So what we can do a circuit like this, in which we put, let's say, a certain resistor so that we are current biased. Typically we can put, let's say, 1 kilo ohm. And then here we put a very small resistor of the order of, let's say, 1 ohm. And all these wires are typically copper wires, low resistance, but they carry some resistance. So each time that there is a piece of wire, I will draw some resistance. So let's say here another 1 ohm resistance. And here I put my SQUID like this. And if you think about it carefully, here I'm current biased because this is essentially 1 ohm, okay, of the order of like half ohm when this is superconducting. So this is essentially, so this here, whatever happens here is irrelevant. So the current at this point is set by the voltage that we put here divided by 1 kilo ohm. So this is the current here. And if you look at this carefully, you can convince yourself that this circuit is not current nor voltage biasing the SQUID. And this I will leave as a homework. But you can show that that if I do it like this, you can show that so this is the line. So the line at a constant. If you impose the voltage, we say that it has a vertical load line, and if you impose the current on this graph, it will have a horizontal load line. And if you're in this circuit, you can show that you're actually in a load line that is in a diagonal. And the homework is to calculate what is the slope as a function of these two resistors. And you can show that the slope of this line would be minus R1 plus R2 divided by R1 times R2. Meaning that if the resistance goes to, if these two resistors goes to 0, this thing goes to minus infinity and you have a perfect voltage bias. If these things are very large, you will have essentially, this will go to 0 and you will have essentially a current bias. And in principle, that's it. This is the prescription. Getting small resistors, you get the good load line and you can move on. But wait, how do you measure the current? So you know the current all the way here, but you don't know the current here. And we know to measure current, the simplest way is to add a large resistor and to measure the voltage on it. So let's add this large resistor here. If you add it here, oh wait, you add to the R1 resistor. That's not good. If you add it here, also not good, you add to the R2 resistor. These two resistors are in series, these two resistors are in series. So basically you cannot add any resistor on any of these branches. So what is the trick? How can you measure the current without adding any resistance to this loop? The trick is to add here a superconducting coil, and this coil will generate some field. Once the current passes here, it will generate some field, and this field will generate flux into an array of squids. And I will just draw a couple of them, but you can have, let's say, 100 squids. And on the other side, you have another circuit with another coil, and you ask yourself, you build some electronics that reads the voltage here that is proportional to the flux and tries to keep the flux on the squid constant. So basically, if there is a bit of current flowing here, if there is let's say you increase a bit the current here, you increase the field here, so this guy will try to compensate for that by creating an opposite field. This thing looks like a transformer. So I remind you, a transformer is two coils that are coupled together inductively. And if I have an AC current on one, it will create an AC current on the other. And the ratio between them will be the turn ratio. Here, we don't do that because that would only give us the AC component. But in the type of, we want to do like a DC SQUID readout. So we also need a DC component. And this is why we need to put this array of squids. So the coil generates a field that generates a flux into the squid array. And this is compensated by what is called a feedback coil. Now this feedback coil, if I know the current here, in a way I know what is the current here, right? So in principle, I just moved my problem from here. At the beginning, I wanted to know what is the current here. And now I'm asking the question, what is the current here? What is the difference? The difference is that here I can put a 1 kilo ohm resistor. If I put a 1 kilo ohm resistor here, it doesn't change the value of R1 and R2. It doesn't change the load line of the system. The only thing I have to change is the inductance of the system by adding this superconducting coil. But because this coil is superconducting, it does not add a DC resistance. However, it couples via this feedback mechanism and the squid array, it couples to this loop where I can put a resistor as large as I want. And in fact, in our lab, we use of the order of even 10 times that or 11 times that, so around 11 kilo ohm. And that gives us the resolution that we want. Again, assuming a 1 microvolt noise level, that allows us to detect noise that are currents that are below 1 nanoamp, which is very good. In practice, our noise level is even better than this. So here I took 1 microvolt as such, but in principle we can play with this. So this will essentially play with the gain. So the current that flows here is equal to the voltage that you measure here divided by this resistance and another turn ratio, because these can be winded so that, let's say, typically there is less turns here, so you need more current to generate the same field. and therefore you gain even more gain, okay? And when you put all this with the gains together, we end up having a noise sensitivity here of the order of 10 picoamps per square root hertz, which is enough to do our SQUID readout. And in our specific case, this is the SQUID on tip. This allows us to get a single electron spin sensitivity and even better.